you two champions, a very good morning to all of you. So today you have your second pre-board chemistry examination, and in this video we are going to do the most important questions from all the chapters. So now see, if you have done the complete revision, you have completed all the chapters, then also this video is very important for you to revise the most important questions once again before the examination. And if you have not completed the syllabus, if you're half done, then also this video is very important for you because you can understand the most important questions, you can prepare them, and there's a high probability that these questions can be asked in the examination and you can score well. So let's get started with this video, and I want all of you to go through the questions and just note down them in short form so that you can just revise them. Okay, and I will be providing the PDF of this in our WhatsApp channel. The link is there in the description section, so please go and join our WhatsApp channel first. Okay, so now let's see the syllabus. We have these 10 topics, okay, and you can see that there are certain topics that I have highlighted in yellow, right? So I have told you in the first pre-board also, if you do these 6 chapters, you can easily score 60 plus out of 70, okay? But in this video, we will be covering all the chapters and their important questions, important formulae, concept, so everything we will discuss in detail, okay? So first of all is solutions chapter. So just a minute, 1 second, okay. So in solutions chapter, the first thing, very important that you should know is 2 laws, that is Henry's law and Raoult's law, okay. This definitions you should learn as it is given in the textbook. Please learn the exact words, the exact definition. So Henry's law states that at constant temperature, the solubility of the gas is proportional to the partial pressure. And here you also need to write the formula. P of the gas is equal to Kh into mole fraction of the gas. And here one more thing you should know, that Kh is indirectly, or I can say inversely, proportional to solubility. Okay. Now what is Raoult's law? Raoult's law states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to the mole fraction present in the solution. So students, I'll be going a little bit fast here because we are going to cover all the chapters. So yes, just go through these questions, these terms that I have mentioned in the question. Next is the difference between ideal solution and non-ideal solution. Very important. Obeys Raoult's law, does not obey. V mix equal to 0, here not equal to 0. Delta H mix equal to 0, not equal to 0. AB interactions are equal, these are not equal. Then here examples are important, so you should know at least 2 examples from each category. Next is we have positive and negative deviation. Again, this is important question. Positive and negative deviation, AB interactions are weaker here, AB interactions are stronger. Here the partial pressure is more, the total pressure is more than the expected value. Delta V mix is more, delta H mix is more. And these are the examples, and these are the examples for negative deviation. Now here also you should know something, that is the graph you should know how to draw. So for positive deviation, if I have like this is for ideal solution. In positive deviation, the graph will be more than the original line. Similarly, in case of negative deviation, what will happen if you have a graph like this? So just let me draw. So if I have a graph like this for ideal solution, then negative deviation, there will be depression in the curve. Okay, so please check these graphs from your textbook. Next, we'll discuss some important reasoning question, that is why the vapor pressure decreases on addition of solute. Now let me explain you this one. So what happens on adding a non-volatile solute, it occupies the, see how the vapor pressure is created. When the surface is there, the solvent molecules will evaporate and it will create vapor pressure. Now when you have added a solute, the sum of the surface particles are covered with solute particles, right? Now if solute particles are present, less number of solvent molecules will evaporate, and that will cause a decrease in the vapor pressure. Next, why boiling point increases? Now see, boiling occurs when the vapor pressure equals the atmospheric pressure. Okay, if the vapor pressure and atmospheric pressure are equal, then at that temperature boiling takes place. Addition of a non-volatile solute lowers the vapor pressure of the solvent. So when you add a non-volatile solute, the vapor pressure decreases. So that is why you need to heat the solution to a higher temperature so that its vapor pressure with the atmospheric pressure can match. Next, why the freezing point decreases on addition of a solute? The same thing, you have to write freezing occurs when the vapor pressure of the liquid is equal to the vapor pressure of the solid, but addition of a solute decreases the vapor pressure. Hence, equality of vapor pressure is attained at a lower temperature, resulting in the decrease in the freezing point. Next important thing is about azeotropes and what are maximum and minimum boiling azeotropes. So azeotropes are binary liquid mixtures having same composition in the liquid and vapor phase, and they boil at a constant temperature and are called as azeotrophs. Minimum boiling azeotrope, the solution has a lower boiling point than either of the components. Maximum boiling azeotrope, the solution has a higher boiling point than either of the components. Next, it is shown by positive deviation. This is shown by negative deviation, and this is example which is very, very important. Okay. Now, seventh one is what is molarity and how does it vary with temperature. So, molarity definition is the number of moles per liter of the solution, and when temperature increases, the volume increases and molarity decreases. So, molarity here formula is number of moles by volume in ml into 1000. Next is osmosis and reverse osmosis. So, movement of solvent molecules from its lower concentration to its higher concentration through a semi-permeable membrane is called as osmosis. Now, what is reverse osmosis? The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. This is now the pure solvent flows out of the solution through the semi-permeable membrane, and this is called as reverse osmosis. Okay, and what is the application of reverse osmosis? In the desalination of water. Okay, one more thing that I want all of you to prepare, which I have left here, is the 3 applications of Henry's law. Okay, this is important one, the scuba diving one, the carbonated drinks, and the anoxia thing that happens when the people go to a higher altitude. Now, next is what is abnormal mass and Van 't Hoff factor. Abnormal mass is the wrong mass that we calculate, and this happens because of the association and dissociation of the solute particles. And how do you define Van 't Hoff factor? It accounts for the extent of association or dissociation, and any one formula you can write down from here. Next is the numericals on colligative properties. So I have not taken numerical questions. For that, you can watch my MIQs video quickly. But here I'll be talking about the formula that is required. If you know these basic formulas, you will be able to solve the question. For relative lowering of vapor pressure, P naught minus P by P naught is equal to XB. And if you have an, I can say, electrolyte, then one I term will be used, which is your Van 't Hoff factor. Elevation in boiling point, delta T b equal to KBM, delta T b is equal to I dot KBM. Depression in freezing point, delta TF is equal to Kf dot m, delta TF is equal to I dot Kf dot m. Osmotic pressure, pi equal to CRT, pi is equal to I dot CRT. Okay. Now moving to the next chapter, electrochemistry, the first important question is Faraday's first law and Faraday's second law. Okay, Faraday's first law says that the amount of chemical reaction that happens depends upon the amount of charge passed through the electrolyte. And here also I will request you to read the exact statement because this is what is given in your NCRT. So please use that statement only. And the formula is M is equal to Z dot IT, where Z is equal to electrochemical equivalent, I is the current, and T is the time. Now how do we calculate Z? Z is equal to molar mass, okay, molar mass divided by N into 96500. And what is N here? N here is the number of electrons exchanged in the reaction. Next is Faraday's second law, and it states that when same amount of current or electricity is passed through two different electrolytic solutions, the masses of the substances deposited or liberated at the electrodes is directly proportional to their equivalent masses. And the formula we have here is M1 by M2 is equal to E1 by E2. Okay. Now, next one is Kohlrausch's law and its application. So, Kohlrausch's law states that the molar conductance of an electrolyte at infinite dilution is equal to the sum of the ionic conductance of respective cation and anion. Means, for example, if I have the molar conductance like this NaCl, that is equal to the molar conductance of Na plus and the molar conductance of Cl minus. Okay, both cation and anion are equally required. Next, write the cell reactions of Daniel's cell. So that you know here zinc gets converted to zinc 2 plus, okay, and copper 2 plus gets converted to copper. It is solid, this is aqueous, and this is solid. Okay. Next is SHE working and its cell notation, very, very important. First of all, this diagram is very important, so please practice this diagram. Next, the standard hydrogen electrode consists of a platinum foil, and it is coated with finely divided platinum. The foil is connected with platinum wire with mercury. Okay, you can see here there is a platinum wire connected with mercury. A copper wire is connected from the mercury for the external circuit. The platinum foil is dipped in the solution, and this is the equation of the hydrogen, the reaction that happens here, that is hydrogen gains electron to give you H2. Next, what is the cell notation? You can write down any cell notation. And one more important thing, SHE is used as a reference electrode and the E naught value for SHE is 0 volt. Okay. Now next one is your fuel cell and its working. So first of all, again, this diagram is very, very important. Fuel cell. In hydrogen oxygen fuel cell, the electrical energy is produced by the combustion of hydrogen as a fuel. Okay. In the general cells where we have seen, the redox reaction was used to convert to chemical energy to electrical energy, and that chemical energy was coming from redox reaction. But in fuel cell, the chemical energy comes from the combustion of the hydrogen and oxygen. Okay. And hydrogen and oxygens are bubbled here. The catalyst, finely divided catalyst is used, and hydrogen is passed through anode and oxygen is passed into the cathode. Okay, this is very, very important diagram. Next is, what is primary and secondary battery? Very simple question. Primary battery is one which cannot be recharged, and secondary battery is one which can be recharged by passing current in the opposite direction. Example, dry cell, mercury cell, lead cell, and nickel cadmium cell. Next, what is corrosion, and mention the methods to prevent the corrosion. So first of all, is corrosion is an electrochemical phenomena. If it is asked to explain with rusting, you can easily explain that rusting, what happens, suppose this is a rod, okay, from here Fe, okay, undergoes oxidation and leaves the electron and moves as Fe2 plus, right? So that is the first thing that happens at the oxidation or at the anode. The electrons move, now these electrons move to a different area where oxygen is reduced. Okay, so oxygen gains this electron to give you water molecule. Next, the ferrous ions formed are further oxidized to give you Fe2O3. Okay, these ferrous ions which is produced here are further oxidized to form the hydrates Fe2O3.XH2O. Since oxidation and reduction occur simultaneously at different sites, corrosion of iron is an electrochemical phenomenon. Now next one is how to prevent corrosion. So for that you have so many methods like painting, okay, then you have greasing, okay, so this is the one method. The second one we have is painting, greasing, and then we have we can use galvanization. Yes, galvanization. Okay, clear? Now next one is question number 8. Direct measurement of conductivity of ionic solution by Wheatstone bridge is not possible. Give reasons and what is the solutions to that. So the first problem is direct current. If it is used, it changes the composition of the mixture, and solutions cannot be connected to the bridge like solid conductor because these are liquids. So what is the solution to that? For direct current, the problem can be solved by using alternating current. And in the solutions, because it is solution, it cannot be conducted to Wheatstone bridge. What we do is we can take this solution in a special type of cell called as conductivity cell, and these conductivity cells can be connected in the Wheatstone bridge. Okay. Now there are some important formulas that I want all of you to remember so that you can solve the numericals from this question. The first one is Faraday's first law, M is equal to ZIT. Oh, sorry. Okay. Next one is Faraday's second law, M1 by M2 is equal to E1 by E2. Resistance R is equal to rho L by A. Resistivity is rho A by L. Cell constant G star L by A. Conductance G equal to 1 by R. Conductivity K kappa is equal to 1 by R into L by A. Molar conductivity is equal to kappa into 1000 by C. Okay. Now, before going to the next thing, there is one important, okay, first of all, please take a screenshot of this one. Yeah, this formula is very important. Now, I'll be discussing another concept that is your that is, just let me write down here, effect of dilution. Okay, please note down this one. Okay, effect of dilution on kappa and molar conductivity. Okay, so what first thing is, when dilution increases, okay, kappa value decreases and molar conductivity value increases. Now molar conductivity increase we will study in two cases, for weak electrolytes and for strong electrolytes. Okay, in case of weak electrolytes the increase is more, and in case of strong electrolytes the increase is less. What is the reason for that? In weak electrolytes dissociation increases, so that is why number of ions increases. Okay, number of ions increases. In case of strong electrolyte, what happens when you have a very strong electrolyte? So what will happen in that case? When the in that case the only thing that happens is the mobility of ion increases. Mobility of ion increases. So this is done. Next here you have a graph for that one, that is lambda m on this side and root over of C on this side. So for strong electrolyte, the graph comes like this, and for weak electrolyte, it is like this. So you can see for weak electrolytes, as the concentration decreases, the change in the molar conductivity is so huge. Whereas in case of strong electrolyte, it is not that intense. Okay, that is something that you should know. So now I'll just clear this one. Please take a screenshot or pause the video, understand it once again. And now we have these things. Let's move to the next chapter here. Here also numericals, all the numericals you can solve if you practice this many formulas only. Okay. Now moving to kinetics, the first very important question is factors affecting the rate of reaction, concentration, temperature, and catalyst. Next is derivation of zeroth order reaction. This I'll just explain in short. So suppose I have a reaction, R gives me P. Okay. Then what I can write for that? See here, you can write rate is equal to minus dr by dt and rate is equal to k into r naught. So these two equations will be equal. Now if to integrate on both sides, you can do a cross multiplication, and when you integrate on both sides, you will get r is equal to minus kt plus I. Now to find this value of I, what you have to do? You have to substitute t equal to 0 and r is equal to r naught. Now when you substitute this, you get I is equal to r naught, and you will get this equation, which is the final equation. Now coming for derivation in the first order, so here also you have to understand reaction is like this. R gives you P. Okay, just a minute. R gives you P. So rate of the reaction minus dr by dt is equal to kr, and you also have that equation that minus dr by dt is equal to just k into r, right? Because it is a first order reaction. Now this equation, and we have this is one equation, and we have another equation that is minus rate is equal to minus dr by dt. Okay, and we can also write rate is equal to k into r, right? So these two equations can be equated to get final this equation. Then you can integrate on both sides, and after that you will get ln r is equal to kt plus I. Again, to find the value of this integration constant, substitute t equal to 0 and r is equal to r naught. Once you do this and then just arrange the equation, you will get the final equation for the integrated first law. Okay. Next is derivation of first order in gas phase reaction. This question was asked in last year pre-board exams, and many students did this mistake because they didn't study or they didn't give focus to this gas phase word which is given to you. Okay. So in gas phase reaction, what you have to assume that the reaction is like this. A gives you, okay, suppose you have a reaction like this. A gives you B plus C. Okay, I'll show you first of all, then it will be more clear. Yeah, you can see here A gives you B plus C. Now T equal to 0. So at time T equal to 0, pressure is P1 and the B value is 0, C value is 0. Now from here X amount will be reduced. Okay, here X amount will form, here X amount will form. Now what will happen, where P1 is the initial pressure at time T equal to 0. The total pressure at this point of time is the addition of all these terms. So that is equal to Pi plus X. Now the X value can be written as P total minus Pi. Next, when you see when PA is equal to PI minus X, so just substitute the value of X here, you'll get 2 PI minus PT. And then if you just write down normal, I can say the first order rate equation, then you will get this term. Next is effective collision, factors affecting effective collision. So you need sufficient energy and proper orientation. So orientation barrier is there and energy barrier is there. Next, show that half-life period of a first order reaction is independent of its initial concentration. Okay, so if you see what is the integrated rate law for a first order equation, integrated equation is K equal to 2.303 by T log of A naught by A, right? Now at half-life or at T equal to T half, that is half-life, A value should be equal to A naught by 2. Okay, now you can substitute here K equal to 2.303 by T log of A naught by 2. Now this 2 will go up, so you'll have 2.303 by T log of 2. That is equal to 2.303 log 2 is 0.301 by T, and you will get this. I'm substituting as T half, okay, because this is half-life. So now if I just multiply this one, I'll get 0.693 by T half, or I can write T half is equal to 0.693 by K. This is the final equation that I will get. Now in this final equation, you will see that there is no A relation with A value. Okay, so that is why it is independent of the initial concentration. Next, Arrhenius equation and graph for all the terms. So Arrhenius equation is K equal to A into e to the power of minus EA by RT. And here all the terms, K is rate constant, A is frequency factor, EA is activation energy, R is gas constant, and T is absolute temperature. Now, if you see the graph for Arrhenius equation, okay, this graph stands for, remember, this graph is for Arrhenius theory, where it says that when two molecules collide with each other, one activated complex is formed. After that, they get converted into product. This is Arrhenius theory and not for Arrhenius equation. Okay, if you want to draw the graph for Arrhenius equation, this is what we have to draw. So I have this equation, right? A equal to sorry, one second. Yes. So what is the equation I have? K equal to A into e to the power of minus EA by RT, right? Now if you take ln and then convert it to ln K is equal to ln A minus EA by R into 1 by T. So this is equal to y is equal to C minus M into X. So the slope of the equation is minus minus EA by R. Now next question is about Boltzmann distribution curve. So when the temperature increases, the number of particles having energy more than the activation energy increases. Okay, and that is why the rate of the reaction increases. Next, the effect of catalyst. So when you have a catalyst, it reduces the activation energy, and that is why the rate of the reaction increases. Now here one more important thing, I want to write down the formula for Arrhenius equation for two different temperatures. Log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. Okay. Next, we'll talk about D and F block chapter. So first of a very important question, and every year it is repeated, is the manufacture of K2Cr2O7. So first what happens? Iron chromate is converted to sodium chromate, and then sodium chromate gets converted to sodium dichromate, and sodium dichromate gets converted to potassium dichromate. Next, KMnO4 preparation, we have MnO2 gets converted to K2MnO4, and MnO4 2 minus gets converted to MnO4 minus. Now this is one method, and you also have another commercial method where MnO2 is fused to give you MnO4 2 minus. After that, electrolytic oxidation takes place to give you MnO4 minus. Next, we have interstitial compounds. Why these transition elements form interstitial compounds? So not why, what are the properties of interstitial compounds? So first of all, they have high melting points, they are chemically inert, they retain the metallic conductivity. And what is interstitial compounds? So in these transition elements, there are certain empty spaces which are filled by smaller atoms like hydrogen, carbon and nitrogen. Next, why the transition elements form complexes? So small size, large ionic charge, and the availability of d orbitals. Next is why transition elements show catalytic activity, variable oxidation state, large surface area, presence of incompletely filled d orbitals, formation of intermediate compounds, and one example is there for vanadium pentoxide. Next is what is lanthanide contraction and its consequences? Steady decrease in the size of the lanthanides is called as lanthanide contraction. Then what is its reason of this one? That is the poor shielding effect of 4f electrons. Now consequences, radius of zirconium and hafnium is almost same, and basicity decreases from lanthanum to lutetium. Next, study of actinoids is difficult. So actinoids are radioactive elements. Half-life of the actinoids are very short, and they could be prepared in nanograms. Okay, so this is the study of actinoids. Okay, next is magnetic moment formula. You should know magnetic moment is equal to root over of n into n plus, where n is equal to number of unpaired electrons in the molecule. Okay, now there will be might a question like, suppose a particular compound is given, it is color or colorless, okay, based on the color of the compound. So remember, whenever you have an unpaired electron, okay, if there is unpaired electron, then there will be dd transition. Okay, now if there is dd transition, the compound will be colored. Okay, so any colored question comes, just check if there is unpaired electron or not. So now let's move to the next chapter, coordination compounds. The first important question is Werner's theory, very, very important. Primary valency, secondary valency, you have to write down. It is ionizable, non-ionizable, and satisfied by negative ions, satisfied by neutral and negative ions, and it also corresponds to the coordination number of the metal. Next is IUPAC nomenclature. So I will solve here one example just to show you how to do the nomenclature. You have to practice the other questions. So you can see here all the ligands should be named first in alphabetical order, right? So you have here diamine, okay, then you have chlorido, okay, then we have nitrito N, okay, and after that we have platinum. Now for platinum, the oxidation state has to be written here. So you can write down for amine it is 0, chlorine is -1, right? And chlorine is -1, nitrito is also -1 equal to 0. So and for metal let it be X. So X here will be equal to +2 and it has to be written in Roman number. So I'll be just solving this one question. Please try the other ones just to prepare how the nomenclature is done. Now let's talk about isomers, very important. So whatever examples are given in isomers for book, in the book, prepare all those examples, nothing else will be asked, the same examples will be asked again. So first of all, for the compound PTNH3 whole 2 Cl2, there is one cis form and trans form. NH3 on the same side, that is cis, NH on the opposite side, that is your trans. Next, coming to CONH3 whole 4 Cl2, here also we will have cis and trans. If you have two chlorines on the axis, then that is trans, and any other configuration will be called as cis. Next, you have COCl2En2. So here if you have En groups, means chlorine groups on the axis, then that is your trans one, and the other all form will be cis one. Next you have this one CONH3 whole 2 NO2 whole 3, NH3 whole 3 NO2 whole 3. So if you have all the NO2 groups on one plane, then it is facial, and if you have all the NO2 groups in one I can say in the square planar structure, then it is called as meridional. Next, for the optical isomers, COEN3 En whole 3, that is optically active because its mirror images are non-superimposable. And here you have PTCl2En2, means if you have this particular structure, its cis form is optically active. Okay. Next, we'll talk about hybridization. This is very important question, but in the first pre-board, this question was not asked. That was quite surprising for all of us, but still, please prepare this type of question. There's a high probability that it will be asked. So first of all, how to write down, first thing you have to do is to write the electronic configuration, and after that what happens, since this is a weak field ligand, okay, for this one is for the molecule COF6 3-, okay, so I'll change this one, give me 1 second. You have to do the same thing for other ligands also, like for any compound COF6 you have +3, right? Yeah, so now what will happen, just check here, that since this is a weak field ligand, so there is no pairing of electrons. Okay, so what are the orbitals available? We need 6 empty orbitals, right? So 3, 4, 5 and 6 empty orbitals will combine to give you 6 sp3d2 hybrid orbitals. Now in this the ligands can donate the electrons, and here you can see there are unpaired electron in the metal, so this is paramagnetic, hybridization is sp3d2, and then you have the geometry is for coordination number 6, it is always octahedral. Now moving to the next one, d orbital splitting. So you should be preparing for the in octahedral field as well as in tetrahedral field. Okay, now please remember what all things are written at the bottom. This is also important. In diagram you need to do proper leveling and then you need to write. Next is metal carbonyls, again important question, so you should know this diagram. So in metal carbonyls there extra stability is there because both sigma and pi bond is formed. Now sigma is formed because the ligands donate electrons, or the donation of electron from the carbonyl carbon to the metal takes place, right? So you can see the MC sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into the vacant orbital of the metal. Now why the pi bond is formed? Now the pi bond is formed because of the donation of the electrons from d orbital to the anti-bonding pi star orbital of the, I can say, metal, right? So the MC pi bond is formed because of the donation of a pair of electrons from the filled d orbitals of the metal into the vacant anti-bonding pi star orbital of the carbon monoxide. Now let's move to haloalkanes and haloarenes. The first very important question is SN1 mechanism. The first step is the formation of carbocation and the second step is the attack of nucleophile. Okay, this question will definitely be asked. See, in the first step what we have, we have a I can say equilibrium arrow, so please check this one. Then a carbocation is formed, this is planar molecule, and then the nucleophile can attack. Next is SN2 mechanism. Here only one step reaction takes place. OH minus attacks from the back. A transition state is formed, and then you have this particular structure formed. Next are some name reactions that you should definitely prepare. Schwarz reaction, very important, is for the preparation of alkyl fluorides. So if you take chloroalkane or bromoalkane with AgF, you will get CH3F. Next is your Finkelstein reaction. Here again alkyl iodides can be prepared by taking alkyl chlorides or bromides with NaI in triacetone. Next, what is a racemic mixture? A mixture containing two enantiomers in equal proportion is called as racemic mixture, and it has zero optical rotation. Next, what are enantiomers? The stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. They differ in the direction of plane polarized light. Okay, so yes, when two compounds are there, they are optically active and they're non-superimposable on each other, then these two pairs are called as enantiomers. Next one is now here three important reactions are there. The first one is your Woods reaction. Okay, I'll just tell you how to remember. In Woods reaction, what happens? Two molecules of Rx reacts in presence of Na and dry ether, okay, to give you RR. Next, second one is in Fittig reaction. Okay, in Fittig reaction, what happens? Benzene X plus Na gives you diphenyl. Next one is your Woods-Fittig reaction. In Woods-Fittig reaction, what happens? One Rx and one ARX reacts to give you a alkyl benzene. Okay. Next, why the less reactivity of aryl halides? We have three important reasons: resonance effect, sp2 hybridization of the carbon, and instability of the phenyl carbocation. Zaitsev rule: during elimination, more substituted alkene is formed as the major product. Next, let's move to alcohols, phenols, and ethers. Here also some important name reaction. Cumene process for the preparation of phenol is very, very important. So first we take cumene there, then we oxidize it to give you this cumene peroxide, and after that on hydrolysis you get phenol, and the byproduct is also important, that is acetone. Next is what is Coles reaction. So in Coles reaction, phenoxide ion reacts with carbon dioxide to give you 2-hydroxy benzoic acid. This is the reaction. Riemann-Tiemann reaction, phenol reacts with chloroform and aqueous NaOH to give you salicylic aldehyde. Okay, so this statement you have to see. Next is hydration of alcohols to give you hydration of alkenes to give you alcohols. So first of all, what happens? Alkenes react with the water molecule and gets protonated. Then in this protonated, the water molecule attacks and the product is formed like this, and after that there is deprotonation, removing the water molecule, and you finally get your alcohol. Next is the dehydration of alcohols to alkenes. Here also the first step is the lone pair of oxygen attacks on H plus, and this got protonated, and after that this one will get dehydrated, or water molecule will be removed to create a carbocation. And after that, what happens? The adjacent hydrogen comes here and you will get a double bonded carbene or an alkene here. Next, we'll talk about Williamson ether synthesis. So in this method, what happens? The haloalkanes reacts with alkoxide, sodium alkoxide, to give you ether. Next, Lucas reagent, it is anhydrous zinc chloride, and it is concentrated sulfuric acid mixture. And how it is used to distinguish between primary, secondary, and tertiary alcohols. See, tertiary alcohols will react immediately. Okay, secondary alcohols will react in 5 minutes, and primary alcohols will not react at all. Next is picric acid formation. So you should know the structure of picric acid. 2,4,6-trinitrophenol is called as picric acid, and when phenol is treated with concentrated nitric acid, we get the structure. Next, phenol is more acidic than alcohols. So if you see when phenols are losing the hydrogen, you will get a structure like this. Okay, and this negative charge can actually undergo resonance and is highly stable. So phenols are more acidic than alcohol because the phenoxide ion is stabilized by resonance. Next, let's move to aldehydes, ketones, and carboxylic acid. Here also we have a lot of name reaction. The first one is very, very important. Many times it is asked, HVZ reaction. So carboxylic acid having an alpha hydrogen on treatment with chlorine or bromine in presence of small amount of red phosphorus gives you alpha halocarboxylic acid, and this reaction is called as HVZ reaction. So what is the must condition? You need to have an alpha hydrogen here. Next is Itard reaction, again a very important reaction. Conversion of toluene in presence of CrO2 Cl2 gives you chromium complex which gets converted to benzaldehyde. Next, Wolff-Kissner reduction. If you have any ketone with NH2 and ethylene glycol, you finally get a hydrocarbon. So what happens here? Whatever this bond is there, right? This CO bond breaks to give you CH2 group. Next, we'll talk about Clemmensen reduction. This is also very similar to, I'll say, Wolff-Kissner reduction, but the reagent is different. Here we use Zn, Hg and HCl. Next, Gattermann-Koch reaction. Here benzene or the carbonyl compound reacts with NH2 and then one imine type product is formed, and finally, okay, sorry, this one is actually Clemmensen reduction only. So in Gattermann-Koch reaction, what happens? You have taken the benzene ring and you just simply treat it with CO, HCl and anhydrous AlCl3, you will get CH. Okay, this is the Gattermann reaction. Next, aldol condensation, again very important. Here you need to have at least one alpha hydrogen and then it should react to form you first a beta hydroxyaldehyde or ketone, and when you heat it further you get your alpha beta unsaturated carbonyl compound. Now Gattermann-Koch reaction you can see here in detail. Next, acidity order. Always remember, if you have an electron withdrawing group, it increases the acidity, and if you have electron donating group, it decreases the acidity. Next, phenoxide ion has more number of resonating structures than carboxylate ion. Carboxylic acid is stronger than the phenol group. Now, the reason we are here is in phenol, what happens? The resonating structures that are formed, okay, the resonating structures in that the negative charge comes on the carbon also, not only on the electronegative atom but also on the carbon. And one more thing, the resonating structures here are not equivalent. But if you talk about the carboxylic acid, okay, you will get one resonating structure like this and the other one will be something like this, where I will have, okay, so both the resonating structures are equal and the negative charge is on the electronegative atom here. Okay, next is amines. So first of all, Gabriel phthalimide synthesis, very important. This one please prepare and go at least 2 to 3 times. You should write in your notebook and then prepare. Carbylamine reaction, it is used for a test for primary amines. Okay, please remember, used as a test for primary amines when primary amines are heated with chloroform or alcoholic KOH. Next, pKb of aniline is more than methanamine. So aryl amines are less basic than aliphatic amines. The reason here is in aryl amines what happens, we have this NH2 group and the lone pair of this one is dispersed, or I'll say undergoes resonance, and that is why the I can say that the aniline here is delocalized, the lone pair on the nitrogen is delocalized and is not available for donation. Next, Hinsberg reagent, you can see here the primary one, okay, the primary amines will react to give you a salt which is soluble. Now why it is soluble? Because of this hydrogen, acidic hydrogen present. Next, again with the secondary amines, the salt is formed but it is insoluble. The reason, again, there is no acidic hydrogen attached to nitrogen. Next, with this one tertiary amine, what happens? There is no reaction because here there is no H. Okay, next is Hoffman bromamide degradation, and this reaction is very important because this reduces the amides to amines, but there is one carbon less. Like for example, if you see RCONH2 here I have taken, right? This RCONH2 reacts with bromine and NaOH to give you RNH2, means this CO group is removed to give you Na2CO3, NaBr and water. This is very important to reduce the number of carbon. Now let's discuss the most important questions from the last chapter, that is biomolecules. So very important question from biomolecules will be on the basis of the structure of glucose. So the first reaction that was done was with HI and the product that we got was N-hexane, and what conclusion we got here? That glucose has 6 carbons in a linear chain. Okay, I'm just writing. So question will be asked like which reaction shows that glucose has 6 carbons in linear chain, then you need to write down this particular reaction. Next is the next reaction is NH2OH and HCN. Okay, here the reaction shows that the glucose contains a carbonyl group. Okay, now to confirm whether it is aldehyde or a ketone, reaction with bromine water is done, and when the reaction with bromine water is done, you will see that CHO group is converted to COOH group. Okay, next we have acetic anhydride. So this reaction, what does it do? It confirms the, I can say, the carbonyl group present is nothing but aldehyde. That is confirmed here. Okay, next what we do to find out the OH group, it is done with acetic anhydride, and here the product we get has pentaacetate group or 5 esters group, which tells the presence of 5 OH groups. Next, out of that, if you just do a strong oxidation, you will find 2 COH group, and that confirms the presence of 1 primary OH group. Okay. Next, we'll see Howard structure of glucose. So please prepare this too. Alpha structure will have OH at the bottom, beta structure will have OH at the top. Next, sucrose structure also you should remember, and this is a reducing sugar. Now, what is inversion of sugar? That is important. So, sucrose is actually dextrorotatory, but when you hydrolyze it, what happens? Fructose and glucose is formed, right? Now, fructose is minus 92.4, whereas glucose is plus 52.5. So, now what happens? The net rotation is negative or in the anti-clockwise direction. So, earlier sucrose was dextrorotatory, but when you leave it for some time on hydrolysis, the solution now becomes levorotatory because there is a change in the configuration. We call it as an invert sugar. Next, we'll talk about maltose. So you can see here the structure of maltose is important. Please remember, and this also is a reducing sugar. Okay. One more thing, sucrose I have mentioned here reducing. Please correct it. This is non-reducing sugar. Okay. Next, we'll talk about lactose. Again, this is made up of beta D galactose and beta D glucose. This is also a reducing sugar. And maltose is made up of 2 alpha D glucose units. Next, the difference between amylose and amylopectin. This is important question. It is water soluble, water insoluble, 15 to 20% starch here, 80 to 85% starch here. Unbranched chain, this is a branch chain, and here you have C1, C4 linkage within the alpha D glucose units. Here you have alpha D glucose units, C1, C4 for the linear chain, and you have C1, C6 in the branch chain. Next, there are proteins. We'll talk about essential and non-essential amino acids. So we have valine, leucine, isoleucine, arginine, lysine, threonine, methionine, phenylalanine, tryptophan, and histidine. These are essential amino acids, means cannot be produced in the body, right? Cannot be produced in body. Now, what is fibrous proteins and globular proteins? So you can segregate it like this. So polypeptide chains that run parallel to each other are fibrous proteins, which are in spherical shape are globular proteins. Insoluble in water and keratin, and insoluble in water, this is soluble in water. Example, keratin and myosin. Here the example is insulin and albumin. Okay. Now let's talk about the denaturation of protein. What is it? So proteins generally can function at a particular temperature and pH. So when you exactly change the temperature and the pH, the hydrogen bonds are disrupted and the globules will unfold. The secondary structure will get disrupted, but the primary structure remains intact. This is one of the most important thing that you should remember. Example, coagulation of egg white and curding of milk. So now we will talk about vitamin and their deficiency diseases. Every year you get question from here either in MCQs or in one marker section. So you should just know the vitamin name and its deficiency disease. Like A causes xerophthalmia and night blindness, B1, and you should also know their chemical names. Thiamine causes beriberi, vitamin B2 riboflavin causes ciliosis, and a whole table is there. So just revise this, and especially the diseases and the vitamin and their chemical names. Okay. Next, we'll talk about what is non-essential amino acids. We have already discussed essential amino acids. So non-essential amino acids are those which can be synthesized from our body. Example, alanine and arginine. Now here one question is there: optically inactive naturally occurring alpha amino acid, that is your glycine. Okay, because if you see the structure of glycine, you have C, you have COOH, and you have NH2, and both the H and the R group is equal to H. So you can see two same groups are present, so it cannot be optically active. So next is the secondary structure. From here question can be asked, the alpha helix and beta pleated sheet structure. So let's see that. So alpha means when the polypeptide chains undergo helical coil, we get alpha helix, and this alpha helix is stabilized due to the hydrogen bonding between the CO and NH groups. Okay, and in beta pleated sheets what happens? They are also stabilized because of the side chains hydrogen bonding or intermolecular hydrogen bonding between the side chains. Okay, so students, these were the most important questions from all the 10 chapters of chemistry. Okay, so if you have completed the syllabus, just go through this and revise these questions once again. If you haven't studied not completed most of the syllabus, then also please go through these questions and revise them, because there is a high probability that these questions can be asked in the exam. Okay, so wish you all the best, and please go with a calm mind, read the questions properly, and then solve the questions. So all the best, good luck.